Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math basic course, and as always, it is an honor and a privilege to be serving you here today, as it is every day here in my virtual classroom. Step on inside. Section 11.6 in the Big Ideas Math Integrated Math 2 textbook is on surface areas and volumes of cones. We're almost there. 11.7 is the last one on surface areas and volumes of spheres, last section in the book. We're on the second to last section right now. You've made it thus far. Don't crash and burn just yet. I got a lecture to go through with you, unless you want to skip it, and then a 26 problem set with you to go as well. Don't know if it's going to be long or not. I always, of course, hope it's shorter, and we'll see how it goes. Check the timestamps below if you want to find something very specific to your needs. Check the description section down below as well to find the download the PDF of this thing, or the IM2 playlist if you want to find something else with me. I'm going to go and get started with this first page right here, kind of as I did from the last one on pyramids, where I just want to show you that cones are to cylinders like pyramids are to prisms. If I have a cone with the same base area and height of some cylinder, I can pour three cones full of sand into a single cylinder right there, and that'll speak to its volume. Now, the first page that they do here talks about surface area. I'll go back to that, I promise. Let's go to the volume page here just to kind of connect with something that we know. So the volume of a cone is still 1/3 area of base times height, just like a pyramid is, because you can pour 3 cones full of sand into a cylinder, and a volume of a cylinder is area of base times height. Now, the cone's base is always a circle, just like a cylinder's base is always a circle, so you can also write it as 1/3 pi r squared times height, just like pi r squared times height, the volume of a cylinder. So this one example that we have a cone that kind of has a right angle that's made right here, so this represents the height of 4.5 centimeters. The radius is 2.2 centimeters. To find the volume, 1/3 area of base times height. Area of base is pi r squared. Pi times 2.2 squared is that area of the base times the height of 4.5, and take 1/3 of it. They're rounding to the nearest hundredth. You get 22.81 cubic centimeters. They have a couple more examples like that. As long as you have radius and height, you are good to go. And an inverted cone still works the same way. So very basic setup. We're going to do some more of those. Let's jump back and look at surface area. Let's actually look at what you'll learn. Find the surface area of right cones. Find volumes and use volumes of cones. So we just talked about how to find volume. How to use it? We'll see. Probably use it to find missing radii, missing height, use word problems, composite solids, things like that. Surface area, there's a core vocab phrasing that's lateral surface. Lateral surface. You probably heard me say the word lateral facing or lateral area quite often. Now we'll put it into context. You see, a cone has two portions to it. There's a base, which is the circle, and there's the lateral facing, which is this party hat looking portion, the side walls that meet up to the vertex here. A circular cone has a circular base and a vertex not on the same plane. The altitude or height's the perpendicular distance right here. And in a right cone, the height meets the base at the center. So the vertex is right above the center here in a right cone. So perfect symmetry like a party hat. And there's something called slant height. So slant height is this distance that you have down to the cone, to the cone's base's edge. And it goes everywhere along here. It's congruent at every which part because of that symmetry. So I'm drawing into the front of the cone. I could draw behind the cone. There's a slant height, and we'll often be using the letter L to represent slant height. R for radius, H for height, L for slant height, not S, not H. Now, all of that's relevant to what we can do to find volume, and especially here, surface area. So the lateral surface is this party hat portion, and you can actually cut along the slant height and lay it down flat. A party hat laid out flat kind of looks like this right here. And you can find its area because it represents the sector of what would have been a larger circle. And so they have a formula. They have a proof behind that formula, same exact proof that I'd use. Imagine that entire circle, shaded area. What is its area? What's the area of the sector? Well, here's kind of there's a whole formula for the area of the sector right here. Pi RL, pi times radius times slant height. How do they get into that? Well, it's a proportion. The area of this sector divided by the area of the entire circle equals the arc length right here divided by the circumference of the entire circle. They're all in proportion with each other. Now, area of the sector is what we're trying to find. Pi L squared is the area of the whole circle because L, the slant height, is also the radius of this. You see, this is part of cutting. Let me erase this here. This is part of cutting this anywhere on the circle. If I go ahead and cut right along here, that slant height, you're seeing that slant height unfold and show here and here. These are each slant heights of the circle, but they're both radii of this bigger circle. So pi L squared is the area of the whole. Now 2 pi r is the circumference the arc length of this circle as it would line up perfectly with this, the base. When you unfold this party hat, this is the rim that it's going around, and that's the same as the base circumference because it needs to go around the rim of that base. It needs to fill it. So 2 pi r, not the circumference of this circle. 2 pi l is the circumference of the circle. So 2 pi r over 2 pi l can technically, 2 and pi can cancel. You have r over l. Multiply both sides by pi l squared is what they do. So, sorry, those cancel there. And then this cancels with this l, and you're left with pi times r times l all together. And that's how they put it. Pi r l, if you ever forget that, pi r l kind of looks like it spells out pearl, if that helps you come up with it. Okay, so the surface area of a right cone in total. There's the lateral area here, plus the area of that base. There are instances where we won't use the area of the base itself. If you want a true party hat and a hollowed out base, you can remove that part. But I normally actually write it the opposite way, pi rl plus pi r squared. So if you ever see me do that, apologies. But pi r squared plus pi rl. I tend to say lateral area. So here's what I tend to do. Surface area equals lateral area plus base area. So if I ever write pi rl plus pi r squared, same thing. Same thing. That's what we get. And I use 2 letters for some reason for surface area. Okay, so here's an example of that. We have the radius of 4. This is slant height of 6, not the height. Now, the height isn't even used for surface area. It would be used for volume. And we could use Pythagorean theorem to find it. I'm sure they'll do examples of that. So if you want to find whole surface area of the base is pi times 4 squared, which is 16 pi. Lateral area is pi rl, pi times radius times slant height. That's 24 pi. 16 pi plus 24 pi gets you 40 pi, and it rounds to 125.66 square inches. Okay, we already did this page on volume. Let's see where they're going to go next and connect it. Volume of a similar solid, same thing as it is for any solid here. You cube your similarity ratio. When you compare these radii of similar circles, well, similar objects in total, this is 9 times longer than this. Therefore, cubing 3 means the volume of this is 27 times larger than this one. And I'm sure I'm going to come up with an example with the cones if they don't for me on this that I really want to speak onto. Because you might not believe that's 27 times bigger, but I'll show you other ones that you probably won't believe. Okay, anyway, so if this volume is 15 pi, we multiply that by 27, and you get 405 pi. 3 cubed is 27. Okay, next one, composite solid. So here would be an example where I would... Oh, and this is interesting. Oh, this is volume. I'm sorry, this is not surface area. This is volume. Never mind. Forget what I was going to say. We take the volume of the cylinder plus volume of the cone. I stopped because I was going to say, wait, they're going to have us do surface area and they didn't teach us surface area of cone? I don't think so. All right, volume of cylinder, area of base times height. Volume of cone, 1/3 area of base times height. Same base area being a circle. That's good. The height of this one's 5. Height of this is 4. So area of base times height here, 36 pi times 5 gives you 180 pi. And then 1/3 area of that 36 pi would be 12 pi times 4 is 48 pi. 180 pi plus 48 pi is 228 pi, and it rounds to 716.28 cubic meters. I don't know if that's the version of finding volume versus using volume, but it looks like that's it. That's it for the lecture portion. So they don't have a lot to say because there's not much different from what we did before. These are like pyramids in that they're 1/3 area base times height, whatever, but they're also like cylinders in that they have circular bases. So there are a lot of things we've seen before, and let's check it out. Describe the differences between pyramids and cones. Describe their similarities. Well, pyramids and cones occupy 1/3 the volume of their respective older brethren, prism-like solids. Let's see, bigger solids, that's prisms and cylinders. So that's how they're the same. They kind of have that 1/3ness to them. They have a single base. They meet at an apex, things like that. Their similarities, I'm sorry, so that's their similarities. They are different by their bases. And because they're bases, they change a lot of things. One is a circle, one's a polygon. So polygon versus circle. So with the circle, you always use a radius, right? There's a pi, you always use pi. It's pi r squared and stuff like that. The bases all change in other certain ways, and we often don't use pi. Yeah, there are other things regarding slant height and stuff that we didn't get to talk to about with pyramids because we didn't do surface area of pyramids. I think that's saved for IM3. Complete the sentence. The volume of a cone in radius r and height is 1/3 the volume of a, well, that's cylinder. So I mentioned that part on number 1. I'm probably repeating parts of an answer when we say that, with radius r and height h. Okay, guys, we are going to jump into the problem set numbers 3 through 26. Let's see if this goes very swimmingly. If you have questions, always write in the comment section down below. I'd be more than happy to answer, especially if I'm insufficient with my answers here. Number 3. Numbers 3 and 4. 3 through 6. Find the surface area of the right cone. So being a right cone, you have perfect symmetry of this. They are doing surface area already to start. So surface area is lateral area plus the area of your base. This is how I'm going to stick comfortably with how I would write this stuff for my own class. So surface area is pi RL plus pi R squared. So we come up with the radius and slant height for all these. This radius is 8 inches, and this slant height is 16 inches. Slant height is the one that does go up the side, the lateral facing. So the surface area for this guy is pi times radius times slant height plus pi times the radius squared. 8 times 16 is 128 pi plus this 64 pi, which we get 192 pi. And that's in cubic inch. This is surface area. This is square inches. So this is area. Despite the fact it's a three-dimensional solid, I don't know if I mentioned that loudly enough or at all. I didn't emphasize that. This is area. So it's something that you can this is our first time talking about surface area, actually. I didn't really get into it. I apologize on that. I kind of assume we've seen it before. The party hat thing, they unfold it. They laid it down flat. It's about making this net flat drawing of this thing and saying, what's the area? What's the coverage? If I have paint to cover over this thing, what is it? So even though it's a 3D solid, when you lay it down flat, how much two-dimensional space does it occupy? In this case, square inches. Now I'm going to round this thing. 603.19. 603.19 square inches. That's number 3. Sorry about not emphasizing that loudly enough. We are going to do volume, and that will have cubic units, but this one currently is just square inches. Square units. Number 4, this time we have a diameter of 11. So the radius will be half of that, which is 5.5 centimeters. Not very attractive of a value. And neither is this L of 7.2 centimeters. So we'll deal. We have some, I'll be working off the calculator pretty quickly here. Surface area is, in this case, pi RL, pi times 5.5 times 7.2. And that might be a clean number. We'll see. Plus pi R squared. Pi times 5.5 squared. And I don't know what 5.5 squared is. So let me jump to the calculator right now. I'm going to leave it in terms of pi to start with. So 5.5 times 7.2. And 39.6 is nice. It's not sad. 39.6 pi plus and 5.5 squared is 30.25. So I'll do the rest just off screen if I do calculations, which of course I will. So as a whole, that is 69.85 pi square centimeters. And that will round to, let's see, 219.44. 219.44 square centimeters. Okay, number 5. A right cone has a radius of 9 and a height of 12 inches. Notice they said height. They didn't say slant height. And there's a difference. We're trying to find surface area, not volume. Let me kind of just copy paste one of the cones here, and I can use it hopefully later or something like that. Maybe. Just depends on how often I want to draw it. But I'll erase some of these other numbers here. So on this one, they give you a radius of 9 inches. So that's a 9. They give you the height, not the slant height. This is 12 inches. We need the slant height. What's L? Well, this is a right cone. This is a right triangle here. This is a cross section inside of the cone. It's two-dimensional right in there, and we can find what the slant height is. We can use Pythagorean theorem. Or note that it's a Pythagorean triple. This value will be 15. but we got to find L. So L squared is 9 squared plus 12 squared. Like I said, we're going to get 15 out of this. So 15 inches for L. We needed that value. So surface area, pi RL plus pi R squared, pi times 9 times 15. And it's interesting that they didn't have any problems before that, not only not in a drawing, but also in the examples. They completely whiffed on that. So this was something for you to kind of know for yourself. And they just throw it on you. They just call it height immediately. And they trust that you know the difference right now, the first time you learned the word slant height, that you'll know that. So it's a little tricky. It's a little tricky. Anyway, this is 135 pi plus 81 pi, which is 216 pi square inches. So that is the surface area prior to rounding. So 216 pi. And I'm getting 678.58. 678.58 square inches. And that's a rounded answer that I'm sure we're all looking for. Number 6, really more of the same. They have this many feet. Oh, this is a diameter. And they have height again, not slant height. So number 6, I won't draw it this time, but not in full. But the radius is going to be half the diameter, 11.2 over 2. That's 5.6 feet. Height is 9.2. Now, remember, as far as the right triangle goes that we're talking about with respect to the slant height, this is radius that goes here. So not 11.2, but 5.6. We'll actually use that. And then the height of the entire thing is 9.2. I do not know what this value is. It could be, it's not an 8, 15, 17. It might not be a Pythagorean triple. We'll see. We'll see. So L squared is 5.6 squared plus 9.2 squared. No, I don't know if this is a Pythagorean triple. So L squared is, oh boy, I'm going to calculate this one. So 5.6 squared plus 9.2 squared. I'm just going to kind of, oh, that's 116 straight up. Wow. Now, that's not a perfect square, but that's a nice clean number. So L is the square root of 116. We're going to go ahead and use this for our answer set. So surface area is pi times radius times slant height, pi RL, plus pi times radius squared. You can't really get too clean with this thing. 5.6 pi root 116 plus whatever 5.6 squared is, 31.36. I'm just going to leave it like this anyway, given that there's the radical there. They can't really combine very well. So let's see what's going on here. So times pi, that number times pi, plus 5.6. I hope everything's still written correctly. Pi times the square root of 116. Wow. And we get 288.00. I mean, there are other numbers there, but that's the rounding. So maybe this is what they were going for. At least it looks like a pretty clean number as an overall. So this is in square feet. Square feet. That is number 6. Yeah, they really lay those ones on you to begin with because we didn't really start with something quite that ambitious and suddenly we're there. All right, number 7 through 10, find the volume of the cone. So now we're back into familiar territory, rather familiar territory. 1/3 area of base times height, just like the pyramids before us. So we have a radius of 10 millimeters, haven't done millimeters very often, and height, we do want height of 13 millimeters, not slant height, no Pythagorean theorem, no Pythagorean theorem to be had here. So the volume is 1/3 area of base times height, right? So area of base in this case is pi r squared, which is 100 pi. And the height is, is the 13. So volume is going to be 1/3 100 pi times 13. This will not clean up beautifully. We'll leave it, 1,300 pi over 3. This is square millimeters, or cubic. We're at cubic millimeters, and now let's do the rounding of that. So 1,300 pi divided by 3, and we get 1361.36 rounded. 1361.36 cubic millimeters. All right. Number 8, the height is still represented here as the one that's assumed to be perpendicular. There's the 2 meters up that guy, and the radius is 1. So even smaller numbers, I think that might help us out more. Radius, 1 meter. Height, 2 meters. Area of base is pi times 1 squared, which is pi square meters. It's always weird to look at it without the numbers there. So the volume is 1/3 area of base times height. So that's 2/3 pi. 2 pi over 3. 2 pi over 3. It's going to be a little bit more than 2, not much. 2.09. 2.09. I feel like something went wrong. That it's just 2, like, okay. So cubic meters, 2.09 cubic meters. I'm just like, yeah, no, I don't know. Do you trust it? Sure, why not? It looks perfect. All right, number 9. A cone has a diameter of 11.5 inches and a height of 15.2. So we need radius. So we'll take the diameter divided by 2 to get that radius. So radius, half of 11.5. It's bad enough that we have a decimal to begin with. Now we have to get it a smaller decimal, right? So 5.75, this is inches. That's our radius we're going to work off of. The height, and this is height, 15 point is what we want, 15.2. Area of the base, this is like the given stuff. Area of the base is pi r squared. So 5.75 squared. You got me. It's less than 36 is all I know. Close to 34, 33, 33.0625. 33.0625. This is multiplied by pi. So the volume, we do 1/3 area of base times height. I feel like somewhere you could probably divide those things by 3 cleanly. Not the first part. Maybe no, not in the 15.2, I bet. No, probably not clean there. So times the pi. I'm calculating everything right now. We'll just work it out. 526.27. 526.27 cubic inches of volume on number 9. And then number 10, they give you the radius again, which is cool. But they give you the slant height. So, and they call it a right cone to be specific to know that you can kind of work out Pythagorean theorem stuff here. We're not finding surface area, we are finding volume, so we do need the height. So the radius is 3 feet. And given the, I'll draw a basic cone here. Cones are pretty fast to draw. So we need to find h here. H, we have r of 3. We have slant height of 6. That's the information that we have, right? Slant height is 6 feet. So the height, h squared is a part of the Pythagorean theorem part. H squared plus 3 squared equals 6 squared. It is a leg. It is a leg this time. This is not a Pythagorean triple. H squared is 27. H is the square root of 27. That's 3 root 3 if we're going to be exact. 3 root 3 feet is our height. We can find volume as, I'm going to go straight up into it. 1/3 area of base, pi r squared times height. 1/3, 3 squared is 9. 9 times 3 is 27. And 1/3 of 27 is 9 again. So let's do this. Let's do 9 pi root 3. Actually, here, let's do it this way. These 3's cancel, and 3 squared is 9. So 9 pi root 3. That's kind of an exact one. That's cubic feet. And that'll be, we'll find out, 9 pi times the square root of 3. About 48.97. Very close to 49 in terms of cubic feet. Okay, let's find the missing dimensions in numbers 11 and 12. We want to find the surface area with this info that we got. We have the surface area. We're trying to find both the height and the slant height. So let's call it like it is. Let me just copy and paste that, especially with the visual. It's the information and it has the visual, so we know exactly what we're trying to find there. So here's number 11. Given that surface area, we'll start off with the formula to work this stuff out. So surface area equals pi r L, that's unknown, plus pi r squared. So that's 3 pi times L plus 9 pi. If we're going to work things out kind of slowly, I can subtract 9 pi from both sides. And then to solve for L, I can divide both sides by 3 pi. So 75.4 minus 9 pi all over 3 pi. Now that's an exact answer. And I feel kind of iffy on this because I got to find h after, and I got to use Pythagorean theorem on this. And I'm not a fan of rounding early. This will be something I'd have to round early on. I'll give you the approximation because we do need the number, but I'm going to store an exact answer in my calculator on everything that I do here to get this last part. So subtract 9 pi and then divide that whole thing by, in parentheses, 3 pi. I know I'm not showing you it. I'm getting like 5. It says 5.000188473. It's intended to be, I'll do to the nearest hundredth, but 5.00 centimeters is kind of the intention, which means, I'll tell you what, given that this is 3 and this is 5 now, around 5, this is definitely going to be around 4. This is going to be a 3, 4, 5 Pythagorean triple. I'm talking about not rounding early. I won't. I'll let my calculator have this on it right here. And I'm going to calculate with that, but I'm going to write the number 5 on my problem stuff, if that's okay. So it is a Pythagorean triple. This answer will be 4. You get h squared plus 3 squared equals 5 squared, about 5 squared. And then h squared plus 9 equals 25. H squared is 16, and take the square root. You get h is 4. You get 4 centimeters on that one. So I should probably put 4.00. I'm going to see what happens here when we do all that. So I'm going to be squaring the 5, this number. I'll be squaring this number. I will subtract the 9 from there, and then I'll take the square root of this. 4.000. Yeah, so it still has that rounding to it that works out. Sometimes it depends on what the numbers are. I generally don't like to round early. But they clearly had an intention with this problem here. So 4.00 centimeters. Excuse me. Number 12. This time they give you the volume. Volume is 1/3 area of base times height. And this is a cone that's tipped over. That doesn't change that the base is still the circle. And the lateral facing and all that is the other part. So the radius is what we're trying to find. Copy paste it. Okay, there's going to be a little part of that 12 showing up in here. I basically screen grab, if you weren't ever curious as to what I do. So 216 pi. There is pi in this value. The last one just had a decimal. So this is 1/3 area of base. I'll go and write out pi r squared. We're dealing in that. Times the height. 18 divided by 3 is 6. So this is 6 times pi r squared. If I divide both sides by 6 pi, I'll get rid of the pi as well. Divide both sides by 6 pi, that gives me 36 over here. Now, pi's gone now. They cancel here, they cancel there, 6 cancel. You're left with r squared. 36 is r squared, so r will be 6 inches. And it sounds like that's all they're trying to find. Doesn't look like they're asking for slant height. You could find it. But no, they don't want us to. All right. That's number 12. Let's move forward. Almost halfway through the quantity of problems that we got to do. Not maybe necessarily the time. Numbers 13 and 14, we have similar cones. We want to find the volume of cone B. It's a lot like what we've done in some of the previous sets of 11.4 and 11.5. What we got to do is compare corresponding parts, and we have them. The ratio, the similarity ratio, I could divide, say, 8 by 16 of the two diameters, and I get 1/2. That's the similarity ratio of lengths. The ratio of volumes, they're asking for volume. The ratio of volumes, you got to take 1/2 and cube it. We get 1/8. That means that this volume right here is 1/8 the volume of this one. That means we got to make this thing 8 times larger. And I always set them up like kind of in this way to start it. Whatever 1 to 8 is, the 32 pi cubic feet is to this unknown volume of cone B. Cross multiply, and you get 8 times 32 pi, and that will be 256 pi. I feel like they're not rounding these answers here. The first ones were exact, and this one kind of has that exactness to it as well. So I think that becomes 256 for that one. Number 14, This time we have shrinkage from cone A to cone B. Okay, so I'll go faster on the second one. I tend to on these ones. We have comparing heights of similar solids, so they correspond to each other. So similarity ratio, I can say do 10 to 4, which reduces to 5 to 2. It also means 2.5. 2.5. That means cone A is 5/2 the size of cone B. So I could flip it. I could say it in the 2/5 fashion. I could divide by 5/2 or 2.5 that way. Maybe I'll set up the proportion to keep it nice and fair so you don't accidentally confuse it. So whatever 120 pi is right here, excuse me, that is 120 pi. Whatever volume of cone B is here, it compares to the 120 pi, the same way 5 does to 2. Cross multiply, and we'll divide by 5 eventually here. We end up getting 5 times volume of B is 240 pi. Divide by 5, volume of cone B is going to be, excuse me, what is that, 48? 48 pi cubic meters. And at most, you definitely want to say, is it smaller than the other answer? Yes. Oh, I screwed up. I didn't cube it. I cubed the first one. I was going to say, and it looks like it's exactly 40% that value. So hold on, I screwed up. My bad. I was saying something looks way wrong with this answer. All right, let's do it again. 5 cubed is 125. 125 over 8. Yes. Sorry about that. All right, let's do it again. Cross multiply. 125 times the volume. I forgot what I was trying to do for a second. 120 times 8 is 960. And divide by 125. This might not be very clean. So 960. Calculator. Turn it on. 960 divided by 125. 7.68. It's close enough. 7.68 pi cubic meters. Okay. That makes me sound better or feel better about what we were doing there. The other one felt too big. And I was like, hold on a second. Because volume, I'm telling you, you guys might not understand the idea that this thing has to fit basically, I don't know, 15. There are 15 of these that can fit in there because it's 3 dimensions that it fits inside there. It's huge. It's way different. All right, numbers 15 and 16, find the volume of the composite solid. So we have to make sure we still know how to find solids of some of these old guys here. On the first one, we have 2 objects. I can call this object 1, object 2. They share the same base area, so let's just start off with that. Each of them has a radius of 3 centimeters, so the base area is pi r squared. Pi times 3 squared, and we get 9 pi square centimeters. Now, the height of object 1 is 3 centimeters. So to find the volume of that cone, as we've been practicing, we're going to do 1/3 area of base times height. Let's let those 3's cancel out, and you're left with 9 pi cubic centimeters for volume of object 1. Object 2 is just area of base times height. Now, we know the area of the base. We have 9 pi. It's still that circle. The height of this one, see, the height of the whole thing is 10. But we need to find just the height of this part right here. This is 3. Therefore, this will be 7. So the height of object 2, let's kind of write that right here. Height of object 2 is 7 centimeters. So area of base times height straight up for a cylinder is 63 pi cubic centimeters. I wish I didn't have to round at the end, but we'll go ahead and do it in the end anyway. The volume of the total, we add these two, we get 63 pi plus 9 pi, which is 72 pi. Okay, so in rounding, 72 pi, 226.19 cubic centimeters. Okay, number 16, next composite solid. So this one, we have to kind of go off of what they give us. We have a cube, and a circle is inscribed inside of the square top base. That kind of works out because it is a square. We can tell by the 5.1s and all that stuff. So that means that can help us come up with a radius, right? When it comes to second object, and I will call this object 2, we are going to have to find out what this radius is. Pretty straightforward. It's going to be half of 5.1. So let's start with the, let's call object 1 as the cube, object 2 as the cone. The volume of object 1 in number 16, I'll dive straight into that. That is 5.1 cubed, which is something. I don't even know, 5.1 squared. 5.1 cubed raised to the... Where's the raise button here? I already forgot. Where? Oh, there it is. I was looking for an X to the Y button. 132.651 cubic meters, volume of the first object. Now, we are going to cut out this cone volume into there. That's a hollowed out area, basically, right? So for volume 2, let's first find out that radius. We're going to take half of 5.1, given how the square works. Half of 5.1, that's 2.55? Yeah, I think so. Meters. So the area of the base for object 2 is pi times 2.55 squared. Squared. 6.5025 square meters. The height of object 2 is the same as basically height of object 1, although we didn't talk about that. That was 5.1 meters. So the volume of object 2, we're going to do 1/3, it is a cone, 1/3 area of base times height. So do I expect it to be very clean? No. Oh, hold on. I'm missing pi. Pi. I was going to say, this is a cylinder, right? Times 5.1 times pi. Okay, so remember what we're going to do. This is rounded. 34.73 cubic meters. I have that stored on my calculator right now to do. I'm going to be subtracting. I'm going to do this minus that. And honestly, it's okay to round this one early in that this is an exact value already and you're doing subtraction, but I'm going to leave the exact there. I think whatever you rounded this one to, the other one will round appropriately with that. So volume of the total, we got to take 132.651 exact minus what appears to be rounded here, but I'm going to, like I said, do the whole thing. So minus. All right, so here I'm going to get 97. Let's do it here. 97.92 cubic meters. It is a subtraction as we took that part out, but 97.92. Okay, let's move to the next set, or to problem number 17. Analyzing relationships. A cone has height h and a base with radius r. You want to change the cone. So its volume is doubled. What is the new height if you only change the height? What is the new radius if you only change the radius? Explain. So the height, so here's our volume, right? Volume is 1/3 pi r squared times height. Now, I want to double volume by only changing h. So if I double volume, I have to take 1/3 pi r squared times, what's going to double it here? I have to do 2h. Multiplying this by 2 will make this twice as large as it was before. So in terms of their first part, what is the new height? The new height would be 2h. Now, if I want to double the volume by doing something to the radius only, this one gets a little bit trickier because it's something that's squared. I'm just going to put an x in here to begin with, xr squared times height. I want xr squared to give me 2r squared. I need to make sure that whatever I plug in for x, that after I square it, it gets doubled. So let's go ahead and expand that portion. X squared r squared equals 2r squared. I honestly don't even need the r's. I mean, I should have said that earlier. Those cancel. I need the x squared, though, to become 2. So if x squared needs to become 2, take the square root of both sides. X needs to be square root of 2. And I don't think it can be negative because they're saying what's the new radius. So if x is the square root of 2, then r times the square root of 2 is the new radius. I kind of explained it through the math here, but the idea is you're going to square whatever that radius is, and squaring the square root of 2 is what gives you 2 to double it. If you plug in 2 into there, if you make it 2r, you will quadruple your volume because 2 squared is 4. So r root 2 is the new radius. And here, new height would just be the h. To double this and double that, that's what we get. All right, number 18. How do you see it? A snack stand serves that was an alliteration. A snack stand serves a small order of popcorn in a cone-shaped container. Don't pretend like you don't know what you did. In a cone-shaped container and a large order of popcorn in a cylindrical container. Do not perform any calculations. Okay. How many small containers of popcorn do you have to buy to equal amount of popcorn in a large container? Amount of popcorn, 3. They said explain. You need to buy 3 small containers of popcorn to equal the amount of popcorn in a large container. This is because they are a cone and cylinder, respectively, and share the same base area and height, and the volume of a cone is 1/3 the volume of a cylinder with that in mind. So I typed a lot more than you probably would type in that scenario for part A, but I'm explaining it to you there so you can find a way to paraphrase it. Have ChatGPT paraphrase that one for you. Sounds good. Part B, which container gives you more popcorn for your money? Explain. Now, they did not want us to calculate, but if I tripled $1.25, I'm somewhere in the $3 range. That's already more than $2.50. So I would want to buy this one if I want to get kind of my best bang for my buck, my best value here. So, and I know exactly what 125 tripled is. I'm sure you do as well. The point is doubling, even doubling, and I know that's doing math, but even doubling that thing would have it as equal amounts. So which one gets the better value? The large. And that's how most places should work. The larger ones should give you bigger value. They should push you to pay for it. So they made more money as an overall. This is really cheap for them to pop popcorn. The large container gives you more popcorn for your money because tripling the dollar amount of the small popcorn container would exceed the dollar amount, the cost of a large popcorn, whilst giving you equal amounts of food, quantities of food. I don't know if you call it food, but snack, right? Snack. I mean, it said do not perform any calculations. I didn't do volume, but if you triple it, right? I mean, there's some in your head stuff that you're still doing. All right, exercises 19 and 20. Find the volume of the right cone. They don't mean the cone on the right. They just mean to do this cone only. All right, I have a 60-degree angle. So this is a 30, 60, 90 triangle. And when we find volume, we do need height, and we also need radius. So if this is the height at 22 feet, I should probably copy and paste that over. Let's do that. But as that is the case, we can use a special right triangle ratio relationship to find the radius straight up. Okay, so this is a 30, 60, 90 triangle. This is the long leg opposite the 60. So the radius, R is going to be root 3 times smaller than that. So 22 over root 3. Now, I may have full intention to simplify this radical, but I don't think I need to. I'm finding the volume of this thing. So I need to square that. So 1/3 pi R squared times height. And root 3 squared becomes 3. So here's what's going to happen. On the bottom, I get root 3 squared, which is 3, and 3 times 3 is 9. So on the bottom, I have 9. On the top, I have 22 squared times 22. That's the same as 22 cubed. 22 squared is 484. 22 cubed, I don't know. So 22 cubed is 10648. And there's pi, by the way. Don't forget pi. And pi, this is in cubic feet. So let's go ahead and multiply 10648 by pi and divide by 9. And we get 3716.85. Volume's about 3,716.85 cubic feet. Okay. So with that in mind, let's move on to the next one. Number 20. The diameter is 14. Let me copy paste this one as well. The diameter is 14 yards. I do need that radius, and then I'll use the radius to get the height in one of those right triangles with trig. This time there's no special right triangle given the 32-degree angle, but half of 14, let's write that out. That's a 7, right? 7 yards. So we know radius is 7. Now this is also a right triangle where we have to find height. And because it's laid down flat, that doesn't change the fact that this isn't height, the distance from base to that vertex, the apex there. So it's not Pythagorean theorem. We do have to use trig. With a 32-degree angle, we know the opposite. We need the adjacent. We will use tangent. So the radius is half of 14, which is 7. And the tangent of 32 degrees equals 7 over h, opposite over adjacent. H is going to equal 7 over the tangent of 32. Let's keep that exact for now as we do volume. We'll do 1/3 area of base times height. Probably not fully worth it to write this thing like unsimplified or, in that raw form, but in terms of calculating, maybe it is. 7 squared is 49 times another 7 is 343. So 343 pi over, and I got 3 times tangent of 32. So I'll try and type that one out. I'll let you see it. (343 pi) divided by, in parentheses, 3 times tangent of 32. And I believe I'm in degrees. It's my first trig thing to do. 574.82. 574.82 cubic yards. Haven't done surface area in a while, have we? I think we started off with it. I'm sure they're going to have some exploration questions. I probably spoke too soon. They'll probably do it right now. But given those exploration questions, we should be good on that one. So 3716.85 here, and then 574.82 cubic yards on number 20. Let's jump to number 21. Are we going to 26? Okay, so 6 more problems to go. Not even yet at the hour mark. Feeling good for now. You saw what happened last time. Number 21. A cat eats half a cup of food. Typical cat. Oh, twice per day. I thought they were saying a cat is starving itself. That's a typical cat, I guess. Will the automatic pet feeder hold enough food for 10 days? Explain your reasoning. So we have to make sure half a cup of food. Oh, here it is. I was like, oh, geez, how do we find this stuff? Okay. So 1 cup, if 1 cup, well, let's start off with a proportion. I think you guys understand proportions with it. But if 1 cup is equivalent to 14.4 cubic inches, then half a cup, I'll say 0.5. 0.5 cups is equal to how many cubic inches, right? So if you cross multiply, you get x equals in 14.4 times 1/2. So that's 7.2. So you divide by 2. So 7.2 cubic inches needs to be the amount of volume here. The question is, will this volume of these two things exceed? Oh, I'm sorry. That's 1 cup. I'm sorry. That's 1 cup. Oh, half a cup twice per day. Oops. Okay, then I guess I need the 7.2. I didn't go back to look at that. So, okay. So what we start off with, let me start that all over. Okay. If the cat eats a cup a day, half a cup twice per day, 1 cup per day. So 14.4 cubic inches times 10 is 144 cubic inches of food in 10 days. We need to see if our volume exceeds this amount. So this is I assume that's the bottom of the, Is this one of those things like that, or is that a cone here with an automatic pet feeder hold enough. I guess what we can do, I don't really know if that's shown a bottom or if it's cut off right there. It must have to be cut off because it's a it's a pet feeder. Okay. This is one of those frustums. Let's see, what do they call it? A frustum? I think it's one of those frustum things that we had before. Interesting. Let's at least start with the volume of the cylinder. Let's start with object 1 and see where we go from there, because I'm curious to see how this height works as an overall, okay? So for object 1, the volume is going to be area of base. Volume of object 1 is going to be area of base, pi times r squared, times the height of 7.5. Now that is calculator. That's 6.25. 2.5 squared times 7.5. That's 46.875 already. And times pi, oh my goodness. That's going to be 147. Oh, I'm sorry. 144 was the number we were comparing to. I thought we were comparing to something else. 147.26 cubic inches there. It's already exceeded it in just the cylindrical portion. So yes, there is more volume. Should have typed this. There's more volume in the cylindrical portion alone than is needed. We saved the cat. Okay. Sorry about the first part. I didn't know that it was half a cup twice per day, things like that. All right, number 22. During a chemistry lab, you use a funnel to pour a solvent into a flask. I wish they had a drawing. The radius of the funnel, see a funnel, it's like one of these, and it's kind of, a very, very small hole at the bottom. I don't know if they're going to talk about actually having an opening or not. But the radius of the funnel is 5 centimeters and its height is 10 centimeters. You pour the solvent into the funnel at a rate of 80 milliliters per second, and the solvent flows out of the funnel at a rate of 65 milliliters per second. How long will it be before the funnel overflows? So let's pretend like this thing does kind of meet at the bottom like a cone like that. It's a very small opening, small enough that it's flowing out slower than you're pouring it in, which is typical of it's typical of my pancake funnel. Waffle funnel, I should say. The radius is 5 centimeters. The height is 10 centimeters. It's a right cone. Okay. Let's start with this volume. The volume of this cone is 1/3 area of base times height. That's 25. 250 pi over 3 cubic centimeters. Now, let's just leave it exact for a moment. What we're going to do... Yeah, I'll leave it exact. What we're going to do, it says you pour the solvent into the funnel at a rate of 80 milliliters per second. Oh, they tell you. I was going to say, what's the conversion of milliliters to cubic centimeters? And there it is. I don't know if I remembered that. I knew that it had to do with cubic centimeters, but I didn't remember how much. Anyway, you pour the solvent at 80 milliliters per second, and the solvent flows out 65 milliliters per second. That means that there's a net difference. Every second, there's another 15 milliliters that is adding into your funnel over time. Every second is another 15 milliliters because there's less coming out than there is coming. There's more coming in than there is coming out. So every second it's another 15. So we want to figure out as 80 minus 65 is 15. This is the change. It's the net change in fill, in funnel fill, I guess I'll say. We want to figure out how many seconds, 15 times how many seconds will you exceed this? Because remember, this is in milliliters. Now, this is actually milliliters per second, right? Per second, per second, per second. But how many milliliters per second do you get until you match 250 pi over 3 cubic centimeters? Now, every cubic centimeter is a milliliter, right? That's the conversion. So we are in chip top shape there. I'll multiply both sides by 3. I get 45t equals 250 pi. And then I'll divide both sides by 45. I'll get t equals 250 pi over 45. That could reduce to 50 pi over 9. However, at some stage here, we're going to be working, and this is seconds, by the way. Yeah, 50 pi over 9 seconds. However, we're going to go ahead and round it now. So 50 pi over 9. And we're getting 17.45 seconds. About 17, it's rounded because of the pi. 17.45 seconds. How long will it be before it overflows? At that stage, at 18 seconds, you are overflowing your funnel. You know, careful. Chemistry explosions all over the place, right? So, yeah, make sure that you got it all good. All right, number 23. To make a paper drinking cup. Oh, yeah, one of those guys. It's one of the party hat things. To make a paper drinking cup, start with a circular piece of paper that has a 3-inch radius. Then follow the given steps. How does the surface area of the cup compare to the original paper circle? Find measure of angle ABC. Oh, you actually fold. You fold. So, how does the surface area? So, the original circle, the surface area of the original is just going to be pi r squared. It's just going to be that circle. Pi times 3 squared, which is 9 pi square inches. The surface area of the new, there are 2 folds. That leads it to a quarter circle. So it's going to be 1/4 of 9 pi, which is 9/4 pi. Now, the question is, does that thing connect perfectly there? It says open cup. Oh. Sorry, now I get what they're saying about it. I just don't get. When they say open it, I don't get what part opens. Oh, they do say ABC. Huh. I don't get what part opens when I fold. So if I take a piece of paper, oh, it's not circular. 3-inch radius, follow the steps. So I fold inward, I fold inward. It says open up. I don't just unfold the... Maybe you do. Maybe that's what they're telling you. They're saying when you unfold the paper, the bend is still there? Gee, I don't know if that's what they mean. Let me think about what they mean. I might want to cut into a circular piece of paper and see what they're talking about. Give me a moment. Okay, so I'm back. So I did this. I didn't measure anything out. I just took a piece of paper and I cut, not even close to the 3-inch radius here, but I cut it and I did the 2 quick folds. So let's see, this little circle thing. I did a fold here, and then I did a fold here. Whoops. And then I did a fold here, and I have that. And then it says open up, or it says open cup or something. I mean, I don't think they mean open it up like that. Like, that didn't really work out. So I figured, do you take this part, now fold it in like that? I think that's a little too thick. Obviously, this is very small as a paper cup. They did say open it. So I don't know what they... Maybe they mean open to half again, and then fold in right there. I think that would make sense. It's a little bigger in size. Look, listen, this wasn't a 3-inch radius, but there's a paper cup, and if you tape it down together. So probably that one. It's probably that version of that thing right there as far as the cup goes. So what we're doing there, I guess, let's ignore what I put for the new. If what we're doing, I'm going to copy and paste this stuff here to kind of bring back what they're saying. If what we're doing here is boom, 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 boom. This stuff here. Remember, this is the original radius, R. Now, when it's folded inward in one part, the R still exists right there. Just keep that in mind. This is R still. They do another fold. Now, in that other fold, that's just a fold to give a point at the bottom, I guess. And then you do the turn in. So when I'm doing the turn in, my R right there, half that part, now becomes the slant height of this cone. So what was R here, I don't really know what it is on this part. Well, now the whole thing becomes R. So this is R. So when you unfold and put the thing here, that becomes the slant height of the cone. So radius is now there. It's a slant height, but it's the radius. So maybe I'll call that, well, I won't call it anything. I'll just call it 3. So that's 3, and let me erase that, and 3 inches. Now I have a new radius within here. New radius within there. And that radius what are the questions? How does the surface area of the cup compare to the original paper circle? If this guy is the one that makes the surface area, the semicircle, that's the one that makes the surface area around there, then I'll say based off going from here to here, semicircle, so part A, semicircle net drawing equals half the area, then I'll go with that. So if the radii, this is tricky. This is tricky to talk about. So that's part A. Now it says, or not part A, that's the first part. It says find the measure of angle ABC. But I don't know that radius. So this thing folds inward to that. Oh, this height. Hold on. This height is also a radius here. So this height, no, excuse me, that height's a slant height. Sorry, I'm thinking out loud about what I have here. I have slant heights. The diameter is just, oh, okay, I have this. So this would be the circumference of the base. So this here is the same as this here. And this would be its own little 2 pi r. And we can find out what this is because this is half of this right here. So this is a full circumference. So the circumference of the original is 2 pi times 3, which is 6 pi inches. And so half of the original is half of 6 pi, which is 3 pi. And that is this. So that means that is this. So 3 pi inches. So if 3 pi is the same as 2 pi r, divide both sides by 2 pi, and you get r as 3 halves or 1.5. So r is 1.5 inches. Let me just write that as its own line. R is 1.5 inches. So in this guy, we have that. Because what's the question? Find the measure of angle ABC. What I feel I want to do with that is I got to find out what... If I want to find measure of angle ABC, I got to find the measures of one of these angles here. So in a right triangle, in that cone, I have my new radius of 1.5 inches and this slant height of 3 inches. And I need to find this angle here, and that's only half of what the measure of angle ABC would be. Here's A, B, C. But let's first find out theta. Theta is the inverse sine of 1.5. Oh, well, here's the thing. That's inverse sine of 1/2. This is a 30, 60, 90 triangle. So this is going to give me inverse sine. That number is going to be 30. Inverse sine of 1/2, which is 30 degrees. So if theta is 30 degrees, the measure of angle ABC will be double that. Measure of angle ABC is 2 of those thetas, so 2 times 30, which is 60 degrees. So finding that radius within there helped me find this, given that slant height as well. We had to double it to find the whole thing. And you could have also seen it from 30, 60, 90, but inverse trig will also get you where you need to go. So 60 degrees, do I agree? This wasn't drawn to scale, so... Sure. Doesn't look like it, but I think I might have messed up there. Not with the answer. I think I messed up in my cone making. Paper cut making. All right, 3 more questions. I knew these would go very long. Number 24. I need a water refill here. Number 24, a frustum. Oh. By the way, I'll read this here. If you know what I'm talking about, what I'm upset about. In the previous section on 11.5, there was a question on frustum. It's the first time I think I've heard the word, maybe. I can't recall. Can't place a time. But I struggled through the problem. I feel like I got it wrong. I think I got close to the right answer, but I struggled through the problem. I took way more than 10 minutes, I'm sure. This morning, because I did the recording last night for 11.5. This morning, I went to my whiteboard in my classroom. The first thing I did was wrote down that problem again. And I think I got it that time. When I have a clear head, I'm not talking to a camera, I don't feel the pressure of the moment of doing something, I'm going to get something on my own. And what I did was I used another variable at one point. I did, as long as I could express it later. So maybe this is the same thing, but for cylinders. Here we go. A frustum of a cone is the part of a cone that lies between the base and a parallel plane of the base as shown. Yes. Write a formula. Yes, they're asking the same thing. Write a formula for the cone of the frustum of a cone in terms of A, B, and H. Okay, I'm going to try and do this time because I think I did it this morning with the pyramid. So I have a frustum right here. What I had trouble with in the beginning last time was coping with an idea of writing H as only this part, but re-representing H in a different way as the height of what would be the entire thing, and writing some fraction form of that. I'll cope more easily with it by using another variable, and that variable will get replaced shortly once I do a subtraction, once I do a substitution. So this is the incomplete part that's missing, but keep in mind, what's in green is basically a similar cone. Hold on. What's in green here is basically a similar cone to what this whole other cone would be. If I subtract this big cone from the small cone here, then I get the frustum. But what I need to do is represent the height of the overall in terms of something else. And this is where I had trouble dealing with here. It's going to be very easy this time. Let's just call it X. If the whole thing is X, or call this little part X, right? It doesn't matter. If I think last time I called this, here, I'll be consistent with what I did on the board this morning. Let's call this unknown part X, so the whole thing is X plus H. So X is this unknown thing. It's not going to be a part of the answer as an eventual bit. It is just to begin with, and it will be replaced later. Because the first thing I want to do is come up with how these two heights correspond to each other. A and B are corresponding radii for these things. So whatever A divided by B is, other corresponding lengths will be as well. X to X plus H. The first thing I actually want to do is solve for X in this scenario. Get X by itself, because then when I write it in other parts, I can replace it with the letters A, B, and H that are involved in that answer. So I begin by cross multiplying, and I get A times X plus H equals B times X. This is absolutely what I should have done the first time that I was doing this for the pyramid stuff. I might even record the video again, but if you kind of see what I do here, I think it should work out. Now I do have to distribute this A so I can get this X term, not alone, but I can get this X term ultimately working with the X term that's over on this side here. Now if I subtract AX on both sides, I get AH equals BX minus AX. Now X is a common factor in here, and I get B minus A. And then I can take the square root, not the square root, I can subtract both sides by B. I'm not talking right. I can divide both sides by B minus A, and I get X equals A times H over B minus A. So there's a representation for X in terms of A, B, and H. So anytime I use X, and I'll have to for volume, this height and this height, anytime I use X for volume, I can replace it with that. I think I'll save it to replace it, but when the time comes that I need to, I will. So let's call this object 1 and object 2. Here's volume, or here's object 1. Object 2 is going to be the whole thing. So, okay, I hope that's okay. So the volume of object 1 is 1/3 area of base, so 1/3 pi times its radius, that's A, squared times its height, which is X. So a better way to write that, there's never really a better way to write these things. 1/3 a squared x times pi. I don't know. I forget if the variables, maybe the variables go last. Whatever, I'll put pi at the end just so I know that I don't lose it. So there's the volume of the smaller one. The bigger one, it's called object 2. The volume of object 2 is 1/3 area of this base, b squared, pi r squared. See, I already forgot the pi. Pi r squared times the height, that's x plus h. So this becomes 1/3 pi. I think it's worth expanding this one as well, considering I'm going to plug things in for x. So b squared times x. I'm going to keep the pi out and stuff. Plus b squared times h. So I need to do this guy minus this guy, basically, to get the result. The volume of the frustum is this one minus that one. Ooh, I did lose pi. Oh, pi's right here. So, I'll put pi in front. Because here's what I'm going to do, y'all. 1/3 pi exists in both of these. I'm eventually going to factor the 1/3 pi out. And I'll factor anything else out that seems like it'll go as well. I don't think anything else does go out. So let's do it right now. 1/3 pi is going to factor out of here. It even factors out of this one. And I'm left with b squared x plus b squared h. And I have to subtract a squared x. So it's at this time that I think I got to substitute this for x. AH over b minus a. Because I got to start cleaning some stuff up in here. So the volume of F, it's 1/3 pi times b squared times AH over b minus a plus b squared h minus a squared times AH over b minus a. I almost want to have the a's first here, so I might do this -1 factoring thing. You'll see what I mean when it comes to it. I probably should have started with that, though, but it's a little too late. So VF equals 1/3 pi times. Now, if you notice here, I'll write things alphabetically. I'll have a b squared h over, looks like h is a common factor as well, over b minus a plus b squared h. Notice this doesn't have this common denominator, the other ones do, over, or minus a cubed h over b minus a. This is missing the b minus a. If I multiply top and bottom by b minus a over b minus a, then I'll have a common denominator in all three of these. Notice again, h though is a common factor. H is a common factor. I'm also going to factor h out of all three of these. So v sub f equals 1/3 pi times something here times the height. H is also factored out. And I feel like I want to leave height at the end. We kind of do that. 1/3 pi r squared times h, that kind of thing. I'm going to put it at the end. So now I have ab squared plus b squared is going to distribute into this b and this a. I can feel we need to do that. B cubed minus ab squared minus a cubed all over b minus a. Now, I think it's near this time that I want to just kind of swap all signs. If I turn this to a minus b, because I feel better about seeing this as a minus b than b minus a, right? Just kind of lead with the a here. So if I call this a minus b instead, then I can turn this positive, this negative, and this negative. And I want to go in standard form. So I want my positive a cubed to be first. I want this a squared b term to be second, and it's now negative. I want the ab squared to be third, and that's positive. Whoopsie, ab squared. And then I want my minus b cubed term to be last. It's now negative, and this is all times height. This could be a version of the answer if something can't simplify, but I feel like the a minus b, I think this might be a minus b cubed. No, what's? No, it's not. No, it's not. Let's factor by grouping. I want to be sure that I have, I'm just going to look on the inside. A cubed minus a squared b plus ab squared minus b cubed. All right, factor by grouping. You take an a squared out, you get a minus b, yes, plus b squared factors out, you get a minus b here. So this is a squared plus b squared times a minus b. And I'm feeling good about this answer as far as the cleanup stuff goes, because now the volume of this thing is 1/3 pi times, there's a squared plus b squared. Hold on. I don't need the big parentheses. There's a squared plus b squared times a minus b all over a minus b. How did this turn blue? Times height. A minus b's cancel. And now you're left with the volume as 1/3 pi times a squared plus b squared times height. And that's not the same answer as the last one was with the pyramid stuff, but I think that is what your final result would end up being as a result of what it is that we are doing there. I don't know. I could have messed something up again. Absolutely. Because if it's, maybe it should be the same as what we had in the last one. I don't know. I felt kind of good with the stuff and how things cleaned up, but maybe not. Because the last one, I feel like there was supposed to be a plus AB. So, I don't know. It could be, it could not be. At least it's clean. But I think I'm having trouble. I think I'm just having trouble with these ones. I feel like I'm better on just the whiteboard in general. I want to maybe knock through this one more time and see what I have. Whatever A over B is, this over that is, because those correspond. Cross multiply, distribute, subtract, AX, factor the X out, divide both sides by B minus A. Okay, I have that part. 1/3 pi. I'm gonna pause this and go through this. Give me a second. Okay, I sifted through it. Do I see a problem with my answer? No. Do I trust it? Not really. Just because last time I had a plus AB there, and I feel like this probably won't change too much from the last one. Maybe it will, maybe it won't. I'm not sure. Do I trust it? Not necessarily. So maybe it's the second time I botched it, but I'm working through it. Again, maybe pressure of the situation, trying to make sure I get it right the first time. Spent a long time on it again. Oh well. All right, 2 more questions. Number 25. Making an argument. In the figure, the 2 cylinders are congruent. The combined height of the 2 smaller cones equals the height of the larger cone. They tell you that straight up. That wasn't your friend arguing that. Your friend claims this means the total volume of the 2 smaller cones is equal to the volume of the larger cone. Is your friend correct? Well, yeah. What? The combined height. I thought they said the combined volume. I'm sorry. I totally misread that. So, okay, the combined height, your friend should still be correct. So these, when you add these 2 things up, it equals the height of the whole thing, right? So I think your friend's good. Let's kind of get a mathy version of what we're just talking about there. So let's copy and paste that thing over. Oh yeah, let me just copy and paste that thing. Okay. So this height, we can call it like whatever this, this can be like X, and this could be like Y. So H, if this is height here, we can say H equals X plus Y. So what we're doing here, I mean, I'll justify this one. The volume of this, this is the same R, right? Same R. So volume, here's object 1, object 2. So volume of object 1 will be 1/3 area of, area base pi R squared times height plus 1/3 pi R squared times the other height. Now there's a common factor of 1/3 pi R squared, and then you're left with X plus Y. Well, volume 2 is 1/3 pi R squared times height, and height does equal X plus Y, and you can see there that there's a connection. So it looks like your friend's argument works, his claim, H equals X plus Y. So yes, friend is correct. Friend is correct. Okay. Okay, and last question, modeling with mathematics number 26. Water flows into a reservoir shaped like a right cone at a rate of 1.8 cubic meters per minute. So 26. Water flows into a reservoir shaped like a right cone. Okay? The height and diameter of the reservoir are equal. All right, so we have a reservoir. I don't know if it's inverted or not. I assume it is. It's a reservoir. So diameter is the same thing as the height. So that the whole thing's height, like that, and so is that. They're both H's. Basically, we can represent them both as H's, is what I'm saying there. So the radius, which I'll really need, is really the height over 2, which is, I guess, what we'll be working with in a second. Show that the volume is, okay, yeah. So show that the volume is pi h cubed over 12. Well, volume is normally 1/3 pi r squared times height. However, this time, area base times height. However, this time, because the radius is h over 2, we have to do h over 2 squared and multiply by the height here. So this is part A, by the way. So volume is 1/3 pi times, that's h squared over 4 times h. The 3 times 4 in the denominator will become 12. H squared times h is h cubed. So you'll be left with pi h cubed divided by 12. And that shows that that will be the same thing as what we have there. That's part A. Part B. Make a table showing the heights h of the water after 1, 2, 3, 4, and 5 minutes. So I'm going to let my calculator kind of help me out here. I hope that's okay. Where we will be doing height. Based on the height, we can find volume. Now, on a calculator, I have to use the variables x and y. I hope that's all right. So 1, 2, 3, 4, 5. We'll use x and y. You plug in x, you get out y. So on a calculator, what I'm going to do is I'm going to go to y equals equation, and I'll do this pi, and my h will have to be an x, pi h cubed divided by 12. And I'm going to substitute 1, 2, 3, 4, and 5 into here and see what those numbers are. So it's these 5 of the values I get here, 0.26, et cetera, et cetera. So we'll do a couple decimal places. So when h is 1, a height of 1, we get 0.26 in volume, and then 2.09 for the next one, 7.07 rounded for the next one, 16.76 rounded for the next one, and 32.73 for the next one. This is in cubic somethings. I haven't really looked into it yet. Cubic meters. So these are cubic meters of volume. These are the heights in meters of how much is filled up. It's basically at what heights you have what volumes. So part C, is there a linear relationship between the height of water and time? Oh, we didn't yet do... Oh, I'm sorry. Those are after minutes. Those aren't the heights. Those are after minutes. So we have to change this again. We have to do time and what the volume will be at certain times. I forgot they gave us a rate. So let's redo that. But I will come up with an equation with it. Water flows into a reservoir shaped like a right cone, a rate of 1.8 cubic meters per minute. So here's the thing. We're going to do a distance equals rate times time setup for this thing. My distance is my height. How much height is cubic meters. Volume is my distance. So my volume is based on taking 1.8 and multiplying by time. So if volume is 1.8 times time, and it's also pi times h cubed over 12, the heights h of the water after 1, 2, 3, 4, and 5 minutes. So I can use this. This is equal to pi h cubed over 12. This is kind of an equation demonstrating these two things, relationship with each other. And height is a function of time. I want to get h by itself in this equation now. So I'm going to multiply both sides by 12, and 1.8 times 12. I'll go back to that table. I will do the table again. 1.8 times 12 is 21.6. So I get 21.6 t equals pi h cubed. I need to divide both sides by pi and take the cube root of h. So h will be the cube root of 21.6 t all over pi. I don't see where there would be a linear relationship between height and time, but there may be between time and volume, but it says between height and time. I don't think so. So make a table showing the heights of the water after these many minutes. So I'm going to make an equation with this. I'm going to plug in t, and I'll get h. So it won't work that way. I don't know if I was supposed to solve that first because I can tell it will not be linear. But let's figure out what we have here. So t and h, let's go back to that calculator. So back to the calculator we go, and we are going to be doing a brand new equation. So instead of this one, we'll do the cube root. The cube root of 21.6 times time, I'll have to use x here, divided by pi. So now when I plug those things in, I get these numbers here. These are heights after time. So I get 1.90, that's meters, I guess, 2.40 when rounded, 2.40, 2.74 at time 3, at time 4, 3.02 rounded, and 3.25 on 5 seconds later. So the question that they're asking you is this linear? Now, the answer should be no based on the cube root thing that you see, but when you look at this table as well, you know, you can look at the jumps in. These jump every 1 second, whereas this jumps half a meter, and then it's about, you know, 0.34 meters, and then 0.28 meters, and then 0.23 meters. So no, it's losing its bits over time. So part C, is there a linear relationship? No. There is a cube root relationship, I suppose you can say. Now, they say explain why. I don't think they mean explain why mathematically. I think they mean explain why logically. And that's a good question. Look at the funnel again. The flow of water into here is constant, but the flow of height going up will not be constant. How come? Because there's more volume up here later than there is down here. There's more space to fill water up. Imagine filling up this water bottle with water at some rate versus a bathtub. They won't flow at the same height. So as this keeps expanding, this radius over time, basically the cross-section of stuff that you have, the water rate is going to appear to slow more over time. So that's why the funnel, not the funnel, the reservoir continues to expand over time as you fill up water at a constant rate, lessening the impact in change of height over that time. And that's why that happens. That's why that happens there. And that should be the idea of the last question there. I believe that should kind of be the answer as well when we get there. And I hope that us getting to that equation made more sense now that I see what we had to do. It wasn't height and volume, it was height and time. All right, guys, so that ought to do it for this one. This is Mr. Robinson. Thank you so much for watching. I'm frustrated over the frustums. I got to figure out what to do with those as an in general thing. And I don't know, I'll fix those ones at some point. Maybe I'll take pictures of them in the description section down below. You can check and see if I actually put it up by this time. So, guys, take care. Thank you. I'll see you in the next one.